Okay, now see, in this video we are going to talk about the extrinsic semiconductor. The extrinsic semiconductor, as you know now, that it is a semiconductor which is doped with impurity atoms. So they are usually the intrinsic semiconductors that we have, they are a crystal lattice of either germanium atoms or silicon atoms. Now when these germanium crystal is doped with certain impurity atoms or the silicon crystal is doped with certain impurity atoms, then they result into extrinsic semiconductor. Now this extrinsic semiconductor is of two types, N type and the P type. So in N type, the atoms which are doped, they are pentavalent atoms. That means they have 5 electrons in their outermost shells, or they have 5 valence electrons. Examples are arsenic, phosphorus, bismuth. And the P type is where the atoms which are doped or the dopant atoms, I should say dopant atoms, these are trivalent atoms. That means they have 3 electrons in their valence shell. And the examples of these trivalent atoms are gallium, indium, boron. Now let's see what is this N-type semiconductor in more detail. So I've drawn this crystal structure of silicon atom, where one of the silicon atom is being replaced by the arsenic atom over here. As I said, that N-type semiconductor is formed when the dopant atoms which we are using are pentavalent atoms. That means that they have 5 valence electrons. Now out of those 5 valence electrons of arsenic, 4 of the valence electrons are going to form covalent bonds with the 4 neighboring silicon atoms, while the 5th electron therefore remains very loosely bound to this arsenic atom. In fact, the energy required to remove this 5th electron completely and make it free and available for conduction is very low. It is almost of 0.045 electron volt for the case of silicon, and it is 0.01 electron volt for germanium atom. So if you provide only this much of energy to the electron, as you can see, it is 0.045 for the case of silicon or 0.01 for the case of germanium. So it's very low, it's very less value. Okay, so when this amount of energy is supplied to the electron will be then completely, it will break from the arsenic atom, becomes free. And when the arsenic atom loses this 5th electron, the arsenic atom will itself become ionized, positively charged in this case. Now electron is negatively charged, the arsenic atoms becomes positively charged. So on a whole, the crystal, this N-type semiconductor remains electrically neutral. It isn't like, that since electrons are you are getting more number of electrons here by the breaking of this 5th electron. It's not as if this N-type semiconductor has a overall negative charge. It's not so. The atom as a whole remains electrically neutral because the arsenic atom becomes positively charged, or you can say it becomes positively ionized. This is something which is very important. It might be asked as a 1-mark question also, so you must remember this. Now coming to this energy band diagram. So this is the conduction band, this is the valence band. So in the valence band you will have more number of you have holes, and in the conduction band you have electrons. Now you may ask, how are we getting these holes? Right now we talked about that this 5th electron is getting removed. It is breaking from the arsenic atom and is available for conduction. So where this hole is coming from? See, when you are rising the temperature, these other covalent bonds will also break, and that will again release an electron and a hole. So overall, the concentration of electrons is always more than the holes. So as a result, you can say that the majority charge carriers in the case of your N-type semiconductor are the electrons, and holes are the minority charge carriers. That means their number, minority means their number is less, and majority means the number is more. So the number of electrons is more here, and the number of holes is less in the case of n-type semiconductor. Okay, now here, as again coming back to this this energy band diagram. Now here, as I said, just a second.